So my project is about single photon scattering. So how did I end up doing this project? What led me to this project is a question. Do photons scatter like waves? So I know the do part and the like part look similar, but or familiar, but the photon scatter and the wave part looks a little alien. But I will try to make sure that you'll be able to understand it by the end of the presentation. And so before I go on to my actual experiment and experimental setup, I want to talk about a few things that would help understand my experiment. So let's start with light. What is light? When we think about light, we think about sunlight, and then when we think more about it, we think of it as rays, and then we think about waves. But that's pretty much how far we go. We usually, the most we can associate with is light being waves. But light can also be particles. Not only that, recently there's new proposition by scientists that the light can be wave and a particle, both. So let's not go to the both part for now, but let's look at light as a wave and as a particle individually. So to begin with, what is a wave and what is a particle? Well, as those little pictures show us, a wave could be a disturbance that travels through a medium from one location to the other and carries energy, while particle is just a small unit of matter. Now, one thing that I would point out here is that if you would look at the wave and the particle, there's something that I can really tell about particle that I can't do with a wave, and that is the position, the localization. That is, so even if the particle is moving, I can tell that a particle was at a particular location and at a particular time. But I can't do the same thing with the wave because it's going on forever and ever. So I can't say, okay, at time t, the wave is right here. I couldn't say that, but I could say that with a particle. So that's a unique thing about particles that wave doesn't have. So now, how did then scientists first come up with the idea that light is actually a wave? Well, there is this phenomena called diffraction, and there's interference. If you look at the left picture right here, yeah, let's look at the left picture. If you can see that when a wave goes and hits the wall that has a slit, you can see that the wave disperses. And on the right side, it's the same thing, especially in this, up till here, we see the same thing. We see that it disperses, and then it hits a second wall where it hits two slits, producing daughter waves. And these daughter waves are actually overlapping with each other. They're interfering. So that is something that you don't see with particles. Particles are not going to overlap, and especially the diffraction and interference patterns, they can be set to any waves, light waves, water waves, sound waves, but only waves. You can't say this. You can't see this phenomenon with particles. Well, then, how did scientists come up with the idea that light is a particle? Well, we all know who that is. I'm assuming you do. So Einstein was the person who came up with the idea that light can be a particle, and that can be supported by the photoelectric effect. As you can see, that is an atom that has a nucleus and electrons, so these little things are electrons, and as you can see, light coming in is coming up and knocking out the electrons. And now this can only be done by a particle which has a specific frequency and a discrete amount of energy. That's how they concluded that, okay, light is a particle too. Well, now that we know that when I said that light is a particle, what is that particle? It's a photon. So whenever I'm talking about light as a particle, I'm talking about photons. And now at this very moment, we are surrounded by billions of photons. If you can see that example that I'm giving, it's a 100-watt light bulb would be giving that many, look at how many zeros there are, that many photons per second. So that is a lot of photons. So now that we know what I talked about, a wave and particle, and light being either a wave or particle, I'm going to talk about my first experiment with a beam splitter. So how does light as a wave behave when it goes through a beam splitter, and how does a light behave as a particle when it goes through a beam splitter? Now a beam splitter is like a mirror. Now we all know mirror. When we see a mirror, we see light. We know that light goes to the mirror and it gets reflected, and that's how we see ourselves. But what you guys may or may not know is that light actually goes through the mirror. Well, you can say, well, we can't see it because most of the times, well, the mirror is placed against the wall, but the actual reason is because the backside is painted. That's why you don't see the light coming out of the other. But the important point is that light can go through or be reflected from that mirror. So a wave, when it goes through a beam splitter, it can split, and it can split in half, and half of it, 50% of it, can go straight through, and 50% would reflect. And that is an actual beam splitter on the right. And so what does a particle do then? Does particle split like a wave does? No, it doesn't, because a particle cannot be split. A photon cannot be split, so it can either go straight through that or it can reflect, but not both. So now that we know what light as a wave does or as a particle does when it goes through beam splitter, now let's go back to my initial title. I was talking about single photons, right? And then a minute ago, I was talking about so many photons. Then how would I go from a bunch of millions of photons to single photon level? Well, one way we could think about it is maybe can I just dim the light and get single photons? I mean, it looks rational. And I actually thought of it, and I did the experiment. So what I did is I used a laser. I sent it through what we call neutral densities. Neutral densities are essentially used to dim your light. They reduce the intensity. So when I send my laser through neutral density and through a beam splitter, now remember that I was talking about having single photons when I'm dimming the light, or I'm hoping there would be. So if there is a photon, as I was talking before, it should either go through or it should reflect to the detectors and then to the counter. The counter is where I would get the signals from the detector. It'll tell me if there is a photon in that detector or in this detector. So before I actually talk about what results I had, I want to talk about a couple of things that would help understand the results better. So coincidences. What is a coincidence? When we talk about coincidences, we say, oh, two things happen at the same time. And that's when we say that's a coincidence. That's exactly what happens here too. So when the detector gets a photon here and there at the same time, the counter considers it a coincidence. So, and the coincidence can be detected by what is called as a SPAD, which is single photon avalanche diode. It's a detector, and I had worked on understanding about it before I was doing these experiments. Well, now another thing that we need to understand is an anti-correlation parameter. This parameter is essentially based on the probability of finding the photons at the detectors. And for two detectors, the anti-correlation parameter, denoted by alpha, is given by the probability of having a coincidence by probability of having a photon at either that detector or that detector. Now remember how I was talking about coincidence being 2 photons at the detectors at the same time. And now with this experiment, and if I were to be assuming that there are only single photon, it should go either there or there, but not at the both. That means I shouldn't see a coincidence, right? That means, according to this, that should be 0, meaning my alpha value should be 0. You can also get other alpha values that I'm going to show before I talk about the other ones. So that when alpha value is very less than 1, so 0, like I'm talking right now about, I would have single photons, which is what we need. But alpha value could also be 1, which indicates bunches of photons, not just one. And alpha value could be more than 1, which indicates correlated photons. Now these two I'm going to be talking about later because those values come up. And now going back to that one, that is what we're expecting, right, with the dimmer light. And let's see my results. So my results, I got an alpha value of 1. Well, that wasn't what I was expecting. And according to my table, alpha value of 1 means I'm getting bunches of photons, which, if I think about it, it makes sense being 1, because if I don't have a single photon, let's say I'm having more than 1 photons, there's a chance that 1 photon is going to go straight through and the other is going to reflect, right? So then I'm going to have a coincidence, meaning my numerator would be 1. So that experiment told me that, okay, by dimming the light, you're not going to get any single photons. Try a different method. I did. I bought in what's called a BBO, which is a beta barium borate crystal. And a process called spontaneous down conversion. Essentially, in that process, what happens is when I send a photon, a purple photon, through this crystal, it interacts with the crystal and produces 2 correlated photons. And this process is conserved, the energy is conserved in this process, in that the energy of the incoming photon would be equal to the combined energies of the photons that are coming out. Now, I talked about correlated photons, right? So what are these correlated photons? Well, these are like twins. And twins meaning if I know one exists, I know the other exists too, for sure. And that also means that they have the same wavelength, like I was showing here, and they would have same energies. Now that we got all of this, I did the experiment. Here's how I did the experiment. I had the same setup that I was having before, and instead of having neutral densities, I had this crystal. And I sent my photons through the crystal, and I had correlated photons. And now, if we see at the results, I got an alpha value of 60. It's very higher than 1, which indicates correlated photons. I mean, of course. So if you look at that, if those photons are being produced at the same time, then, and the path is the same length, then that means they're always going to reach at the detectors at the same time. That means it's always going to be a coincidence, or most of the times. That's why I got a 60, meaning I have very highly correlated photons coming in. By this experiment, it tells me that, okay, you have photons, single photons, but they're coming in pairs. But I wanted to experiment with 1 photon, right? So how would I go from having a pair of single photons to having a single photon that I want to experiment with? I extended my beam splitter experiment. So if you would, that is the previous one that I had, and now this is where I introduced something, a beam splitter. Now if you look, I have the same laser, and then I have BBO, and those are my correlated photons, and this path remains same. I didn't do anything with it, but here I put in a beam splitter. So this one, remember how I said when I know there's a correlated photons, I know there's one, then if I know there's one, the other is also going to be there. So I'm going to use this photon, the one that is going to go through this path, I'm going to use that as a reference, and I'm going to work with this one. If you see, this is the same setup that I've been having from before. And if anything that's going here through here is a single photon. It should go either here or there, but not at the same time to the both places. Before I go to my results for this one, I want to talk about the anti-correlation parameter again, because it is a little different from the anti-correlation parameter for the two detectors. Now, this is a simplified version of the ones that I was having before, and the numerator says the number of triple coincidences that we observe. And what is triple coincidences? Didn't I just talk about having coincidences? And triple coincidence is when I would have a photon at A, B, C at the same time. But the thing is, I was just telling you guys that the photon can't split, and there are only two correlated photons. So where is this third one coming from? Obviously, it's not getting split. But this third photon is a random photon, which is just happening to be reaching the third detector the same time as the correlated photons are doing. That's why we get a random triple coincidence. And then the denominator is the number of coincidences at A and C, meaning that the photon, the one correlated photon is going to A and the other is going to C at the same time. And the next one is number of coincidences at BC is similar to AC, meaning that a photon is going to B and the other one is going to C. And the NC would be number of counts at C. So the number of photons that my detector C is getting, my reference. My result. So it's 0. Well, remember when I was talking about that being single photons? It makes sense. I mean, if something is going here, it's a single photon, there shouldn't be any correlation at all between those two, because it should be going either this way or that way, but not both. So if you remember that, the coincidence for the two detectors, the numerator is going to be 0. So me getting a 0 tells me that I'm finally having single photons. And yeah, that's how I felt when I actually got them and got them working. Because it's hard. And I'll tell you why it's hard. It's hard because there are problems you'll see, like 3 lasers dying because they gave up, and then laser electronics dying, and then somebody is going to mess with my stuff, like all they have to do is nudge a mirror or nudge a detector, because I'm working with things I can't see. So if they just nudge a mirror and the photon is going this way and my detector is here, I'm never going to detect that. So that kind of makes my alignment challenging, where I have to keep going back and aligning things again. And my counter is finicky too. Sometimes it gives up. It says, well, I'm not going to work with you. I don't care if you have a presentation anywhere soon. I'm not going to work. But that's kind of how I felt too. It's kind of sad. But now that I have single photons, let's talk about scattering. What is scattering? Scattering is when a wave or a particle is dispersed or deflected. Now, if you guys were like me and played with torchlights as a kid, I used to put torchlights under my hands, and I thought it was cool as a kid. I still think it's cool because I know what's happening. What's actually happening is that light is going through our tissues and it's scattering. That's why we see this beautiful thing. Amazing phenomenon. I don't know. I think it's cool. But so that's scattering. Before I go into my experimental setup, I want to talk about Rayleigh scattering. This is important because it ties into my experiment. Now, Rayleigh scattering is nothing but scattering of light off of air molecules. This is actually the reason why our sky is blue in the mornings. And Rayleigh scattering depends highly on the angle and the wavelength of the air molecules. Now, why is this important? Now, we see scattering when Rayleigh scattering especially, we see it when the molecule size, the wavelength of the molecule is smaller than the wavelength of the light. And for the molecules that I'm using, like water, because water is one of my materials, their wavelength is smaller than the photons that I'm using. Wavelength of photons, which is 810 nanometers. This tells me that there should be scattering happening with my photons. Now that's my experimental setup, and the left is the actual picture. And 2 years ago, that was empty. That table was empty. So that's where I came up to till now, building all that. Now, if we look at this one, which is more clear, what's happening is that my light is going through from the laser, through the BBO, and to the detectors. Now, if you see up till here, everything is same as from the previous ones. What I've added is this piece of equipment which can accommodate having a material so that I can send my photon through material. Now, remember when I was talking about correlated photons, I said I'm going to use one of them as a reference and the other I can use to experiment, the single photon. So this is my reference path, and this is the path I'm going to use my single photon to experiment with the material I'm using. And if you notice here, there is an arrow that indicates that I can rotate this mount with respect to the material. Now those are my materials, so that is my material holder. That would be air, water, and diluted milk. Although the first two look pretty similar, I assure you they're not. I didn't use the same picture. So the data. So if we see here now, we see that the coincidences from air to water to diluted milk, they are gradually decreasing. That means that the photons that are going through the material, they're missing. That's why we're not having a coincidence, because if the reference one is going to go to the detector at time t, and the one that is going through material is just missing in action, there's never going to be a coincidence. So that's why we see that the coincidences are decreasing, which tells me that, okay, my photons that are going through the material are not going to the detector. They're going somewhere else. They're missing. Well, they're not really missing. We know what is happening, scattering. We're just kind of building up on that, and finally this is the evidence that they are most likely scattering. And this one is, this graph is an extension to the diluted milk, where I took the 0 being having no milk at all, just water, and this 55 here, there's all milk. Now you don't see any coincidence there because photons can't go through that bunch of molecules tight together. So you can also see that the coincidences are decreasing, which also supports the idea that the decrease is the possibility of scattering. So that answers my question that I had in the beginning. For further, I want to have a better optical setup. As you saw that I have a very tiny material holder, I want to have a better material holder. And then I also want to move my rotating mount and see if I can get the scattering angles. So I know it's scattering, but I want to identify and determine, so at what angles is it scattering? And then I want to compare the scattering of laser with my single photons. Laser is just waves, it's not photons. Laser itself, not going through any crystal or anything. So I want to compare that to single photons. So that would be my project. Any questions? Okay.
Thank you. This was impressive, actually. It's a great project. Couple of questions. One, how long did it take you to gather all this?
So actually I've started this a while ago, but I had to repeat everything since my whatever I had to repeat everything for this project to get because everything has been changed. We've been improving my equipment, so it's essentially the time from last semester then, whenever I started the project.
And how many times did you have to restart? Because you said that
I don't know, probably 100 times by now.
Oh, wow.
like I was saying, it is hard because one, like I was saying, you can't see them, you can't see where they're going, so your only thing you can rely on is the counter, and sometimes the counter gives up too. So it takes a lot of realignment. Sometimes I had days where I would realign everything, I'm having everything perfect, and the next day I would come, everything is messed up. Like all the photons are just gone, the counts are gone, the coincidences are gone, and then I find out that somebody probably had nudged the thing, so we finally put like a wooden plank so so that nobody messes with it.
So you said, I don't know, maybe like three slides ago, maybe, when, yes.
Okay.
Yes, so you did, for the single photon scattering, you did the test on the air, water, and the diluted milk.
Mm-hmm. Different amounts of diluted milk too, as that one is saying. So this is different amounts of milk and water.
So for your water, was that just tap water that you used, or was it distilled water? Or?
It's tap water. That's why we see that much of scattering, because tap water is not completely pure of anything. So it has like ions. It's not pure. So.
And did you use tap water to dilute the milk also?
Yeah. To be consistent.
I'm making sure you were calling on me.
No.
Okay. In terms of your alignment of the optics, what was it like trying to align the 810 nanometer beams? What did you have to do to get things aligned?
So what we had to do is, okay, so what I had to do is I used a laser, and then I sent a laser through, like reverse engineering, I sent them through my collectors back to the crystal to make sure it's centered. And that's how I aligned initially. And then I had to do that for every time I maybe changed the position or I added extra equipment, I did that.
Okay.
Is that your question?
Yeah, that's kind of my question. Yeah, that's very much my question. How did you get it aligned? Just because you have two problems with those photons. There's not a whole lot of them, and it's out of the visible.
There's also, I also had to consult a couple of research papers where I came to know that the photons that I'm looking for, so actually here there's a bunch of photons going through. These are not the only photons that are there. There's a bunch of photons. But I'm selecting these specific photons by the angles. The angle between these is 3 degrees to the center. That's where I'm getting my 810 nanometer photons.
Okay.
So earlier you said that the light is a wave and a photon, right? But is it or and? It's and, right?
That's a hard question because, yes, light behaves as a particle and also behaves as a wave. But some phenomena, it's better, you can understand some phenomena better when you think of light as a wave. And some phenomena, you can understand light better when you think of it as a particle.
Thank you very much.